is you do AD minus BC, flip the diagonals, put minuses on the off diagonal, like so, and this is the formula for a 2 by 2 inverse. Inverse of a 2 by 2 matrix is that. So like here's generically, let me just talk about this kind of like symbolically, what this equation we're looking at is. It's something like this. It's like matrix M times V prime, vector V prime equals to like, you know, G vector, okay? So we're trying to solve M V vector prime equals to G vector. The way to do that is to multiply by the inverse matrix on both sides. So inverse matrix M, inverse M V prime is M inverse G like this. What happens with M and M inverse is they cancel out, and that just leaves us vector V prime is equal to M inverse times G vector. So this is called solving a system of two equations by multiplication by the inverse matrix. So doing that here gets me that V1 prime V2 prime is equal to 1 over Y1 Y2 prime minus Y2 Y1 prime. Why is it okay to divide by that? That's the Wronskian, right? So that's non-zero by assumption. Right? So we can divide by it, which is to say that this inverse is defined. And I have to multiply that by 0 and G over A like so. And so what I get is I get 1 over Y1 Y2 prime minus Y2 Y1 prime. And let's see here. This gives me minus Y2 G divided by A, and then Y1 G divided by A. Again, just to emphasize, what we're looking at here is this is my inverse matrix, and this is my, what I call it, G vector. And this is my, what I was calling vector V prime. Okay, getting to the point here. If I can find a spot to write. We have now reduced this. We got V1 prime and V2 prime. What are they? So we have derived that dV1 dx equals to what? And dV2 dx equals to what? V1 prime is it's minus Y2G divided by A times the Wronskian. Did I do that right? Y1, Y2 prime. Yeah, okay. And then this guy. So therefore, V1 is the integral of minus Y2G dx over A times Y1, Y2 prime minus Y2, Y1 prime, and V2 equals the integral of Y1G dx over A times Y1, Y2 prime minus Y2, Y1 prime. And these guys right here, these are the formulas that you need to memorize for variation of parameters. But not just these formulas, right? You need to understand, I mean, yes, you need to memorize these integral formulas, but also you need to know how to use them. You know, you have to also memorize this, right? Where they're coming from, how you use these formulas, put them in here to construct the particular solution, all right? These are I think these are equation 10 in your book in the relevant section, which I think is section 4.6. later in like section 6.4 or something, he does nth order variation parameters, which, as I said, we don't get paid enough to do in here. I mean, maybe if I was teaching 2 classes instead of 4 classes, I'd do it. I don't know. Whatever. But of course, variation of parameters is a weapon of last resort. On the other hand, it's totally general. See, because the existence and uniqueness theorem says that this solution set can be found for a second order problem, right? And not just that, that it's Wronskian is well defined, right? And identically non-zero, which means this calculation we just went through, while I will typically apply it to the constant coefficient problem, it equally well applies to other problems. So it's a general method. So where undetermined coefficients stops, variation parameter starts. This one here, let's see, let's get it. So we got, this is lambda squared plus 1 equal to 0. So lambda is plus or minus I. May I recommend that we use the solution set y1 equals to cosine x, y2 equals to sine x. It pays to calculate the Wronskian before you get to these formulas. Okay? Think about that. You want to simplify this before you do these formulas, right? Otherwise, you have whatever simplification you got to do 2 times. And in the context of an integral, where you're going to be stressed because like the integral is upon you, you know? So just get the algebra out of the way to start with. y1, y2 prime minus y2, y1 prime here is what? Otherwise known as 1. All right. Also, notice A equals to 1, right? Yeah. And what's my G? G of x is secant x. All right. So apply method of variation of parameters. That's our goal. I mean, that's not very good. Let me restate this. Let's calculate V1 and V2. Where yp is going to be equal to V1y1 plus V2y2, right? Okay, so V1 is the integral of, oh, well, that's really nice, right? Because the denominator is just 1 here. So it's not too bad. It's not always that. It's sometimes something. But here it's not bad. And so we really just got minus y2g, right? Over 1. What is g? What's y2? Oh. So we got minus sine of x times secant of x, right? So that's the integral of minus sine x dx over cosine x, also known as the integral of du over u. So we got natural log, yep, it's the value of cosine of x is my v1. Much like with the integrating factor method, you don't really need to add a constant here. Adding a constant here just adds in another copy of your homogeneous solution, if you look at it. Let's see here. Then V2, what's V2 equal to? Minus, not minus, but y1g over 1, right? This one's funny, right? So you got cosine x times secant x. This is the, for kicks, I should put this on my Calc 2 test today, right? See what they do with it. But I feel so bad if I see somebody spend like 20 minutes on it, right? Torn. It's kind of too late in the semester to tell them, all right, you need to go back to Calculus 1. But I mean, that's what I should tell that person, right? But can I tell that person that at this point? I don't know. I think some of you told me they're just going to change their major, so I should just relax. But yeah, that's just X. Okay, so now we're not done. It's not the answer. We assemble the answer. Hence, y is equal to c1 cosine x plus c2 sine x, right? That's the homogeneous part. Plus, let's see here, v1 y1, which is cosine x. I'll put the cosine x first. Natural log the absolute value of cosine x plus x times sine x. Okay, admittedly, you know, if you want me to be pedantic here, what did I do? I wrote y1 v1, and then like over here, I wrote, you know, v2 y2. But these commute, right? I mean, they're real valued functions. You can do either way. Why did I put the x first because I don't know, just to me, x sine x looks right. Sine x times x, it's just not right. It doesn't matter, of course. This is just formatting, but to me, this is the way I like to see it. And there you go. That is the general solution here. Could we have found this by the undetermined coefficients? Certainly not, right? This kind of particular solution over here, right? This thing is definitely not anywhere to be found. Well, okay, fine. That's something we might have found, right? So that piece is kind of in our realm, but this right here, this is in the upside down or something, right? I mean, but all right. Any questions? Is the method clear enough? If you find a problem that's second order and undetermined coefficients won't take care of it, probably it's a variation of parameters problem.
So like the quadratic formula and it's not simple, but
What's that again?
I'm just kind of thinking of it as like back to algebra when you solve equations with factoring and what have you. It's like the quadratic formula for that.
Oh, this is kind of like the quadratic formula?
Yeah,
Yeah. That's not a bad analogy. This is kind of like the quadratic formula of this realm. Yeah, I like that. I guess this is my example 5. We could solve this. It'd be pretty easy. So this x, to get this x, I could solve. I want yp prime prime plus y, let's say p2, equal to x. I would guess that yp2 is ax plus b, right? What's yp2 prime prime? It's 0, right? So apparently, yp2 prime prime plus yp2 is equal to x, which is to say that yp2 is x. So this one, my p would be yp1 plus yp2. This guy right here, I'm saying is yp1. So to produce a secant, I just do this stuff. To produce an x, I just put x, actually. And so the general solution for this problem would be c1 cosine x plus c2 sine x plus x plus this thing. What did I just use here? What method did I use? What's this called? I just did. What I just used is the so-called method of superposition, right? If you have a differential equation, which you have the same like L for both problems, but you have a different forcing function, you can build the net force by a sum of the forces. This is superposition. We'll talk more about this like next time. That's the next kind of thing we should talk a little bit about. Not a big deal. We'll come back to this idea. Don't sweat it. I know you guys got other classes to go to. It's good. It's all good.